Okay. All right. So who was not here for the first half? Yeah. Okay. All right. So I'm Bryce. I'm Bryce. I work at NVIDIA, and this is a talk about C++17 features. For those of you who have just joined us, the first part of the talk, we covered language changes in C++17, and the second half is going to talk about new library features in C++17. And for those of you who are in the first half of the talk, somebody helped me out during break to adjust the font color, so hopefully the operators are a little bit more readable now. My apologies for the AV and color contrast issues. But again, this is the link where you can go to view the slides right now if you want to follow along on your laptop. And I know somebody from the back of the room had requested making the font a little bit larger. Unfortunately, there's not much I can do about that. So sorry about that, guys. So let's get right into it. So this is the 13 different library features we're going to talk about. And the ones that I have underlined here are sort of the ones that I think are the biggest and most impactful. So the first of them, so the string view, optional, variant, and any are three new sort of vocabulary types in the standard libraries. So let's dive into those. So in before C++17, we would often, when working with strings, write functions that would take a string and manipulate it in some way and then return a new string, but would not actually really modify the underlying string, but just sort of change the way that we were viewing that string. And unfortunately, with something like std_string, which has ownership semantics, writing these sorts of functions like this first three function here, which takes a string and returns the first three elements of it, this can be expensive because it requires you to make a copy, because here I'm using the .substr method to get the first three elements if it has more than three elements, and that might allocate, it might create a new string. And even if we were to take this by value, this might still end up with unnecessary copies. And so then this operation, which isn't really a mutating operation, might introduce additional copies than we really need of strings. So in C++17, we have a new string-like type called string view. String view has the same interface as std_string, more or less. So it has all of the million of member functions that std_string has. But it does not have ownership semantics. What string view is a lightweight, non-owning view of the string. Sorry, I'm going to have to refresh this page because my slide notes are not coming up. There we go. All right. So a std_string view, as I said, it's a non-owning copy, and it can't actually mutate the elements of the string that it points to. But it can be quite useful to work with because when you're taking a string view like here, and when I take a substring of this string view, I'm not actually modifying anything. And the new string view that I can return, it's pretty cheap to copy because it's just like a pointer and a size. And so then this becomes a fairly cheap operation. So it's in a header string view. It's a non-owning view of a string. The interface is mostly the same as std_string. It's often a dropped-in replacement. Std_string might allocate. A string view is never going to allocate. A std_string owns its contents. String views don't own their contents. They're the equivalent of sort of a pointer in the length. And copying a std_string view should be cheap, whereas copying a std_string might be expensive. You should pass them by value, not by reference. But you can't mutate the elements of a string view. And this is to avoid you overwriting the null terminating character, is my understanding. So like in this example here, I've got two different implementations of a splitting function, which takes a std_string and then a regex to look for as a delimiter inside of the string, and then returns a new vector of strings that are the delimitated elements of the original string. So the std_string version here will create a whole pile of new strings and return them in the vector, whereas the string view version will just create views into the original string and won't actually create any new strings and return them in the vector. Yeah.
The owner's string goes out of scope, then what happens to the string view?
The question was, what happens to the string view when the owner string goes out of scope? The answer is, it's just like a pointer and a length. So it's like you've got a pointer to something that's been freed. So if you continue using that string view, you're going to have problems. So string view does not hold doesn't have any ownership of the thing itself, and it will do nothing to protect you from shooting yourself in the foot if the thing that it's pointing to goes out of scope.
Similar question about if the original string changes its contents, the string view will see the new contents?
Yes, so if the original string's contents are changed, string view will see the updates, because it's just pointing to the same memory. So the question is, if the length of the original string changes, will the length of the string view change? The answer is no, because the length is a part of the string view itself.
But if the size of the string changes, and if the relocate to different portfolio, string view will point to the whole part.
Right. So if the original string, if you add a bunch of new elements to it and it gets moved to a new location in memory, then the string view is going to become invalid, and it would not be updated by the string being moved to new memory to accommodate the new size of the string. So there are. It does not have any smarts that protects you from any of these things. It really is semantically sort of just like a pointer plus a length. Yep.
Does string view maintain the pointer plus length? I was wondering about null termination. So it's just it maintains it and doesn't let you go over that. But if you pass that into something else, you will have to copy it in something that's expecting to your terminated string.
Right. So the question was, does the string view have a length, or does it check for a null terminating?
Right. Does it keep like this position or the length or?
So the string view keeps a length and does not look for a null terminating character. Okay. Any other questions on string view?
What if the original string was constant?
What if the original string was const? I'm not certain what you mean.
I mean, can you apply string view to a constant?
Can you get a string view from a const string? Yes, you can get a string view from a const string. Because keep in mind, the string view, you can't modify the elements of the underlying string. So it's not an issue at all there. Something like span from the guideline support library, you can modify the underlying elements of the thing. And so there you can't take a span to a const string, for example. Okay. Any other questions on the string view? Yep. What happens if you do .cstir on it? You'll get back the pointer. Yeah. Is there a dot? Okay. Yes. Yeah. Sorry. So when I say mostly the same, there .cstir is not there. Yeah. But data is there. Okay. Okay, so data is there, .cstir is not there, but data may return a null pointer. Okay. Can you cast a string view to a string? The answer is probably going to be no, but what sort of caster do you have in mind? No. You can't. There are different representations, so you definitely don't try casting a string view to a string. You can construct a string from a string view. Okay, so talked about this. Okay. So one of the other nice things about string view is that you can use it to simplify your interfaces. So like in C++11, let's say that I had this 2int API that takes string representations and attempts to convert the string to an integer. So I wanted my API to work with std string, with like const references to std string, with C-style strings, and with like my own string classes. The nice thing about string view is that because it's this non-owning view, it's sort of agnostic to whatever the implementation detail is of the string. You can just have this one interface, make everybody provide some mapping to string view, and such as like this for your own internal string class. And then this will work for std strings, for C-style strings, and for whatever your own string classes you make convertible or constructible to some way of string view.
So by default, STP strings as an operator that you can get the string view out of it?
You can construct a string view from a std string.
What happens if my string, like the internal implementation of my string, doesn't use a null terminated character array and you try to construct a string view from it? Does that still work?
So the question is, if you try to construct a string view from your string representation that doesn't have a null terminated character, will that work? I believe, yes, I believe it will, yeah. There's string view won't check that the string that it's been constructed from has a null terminated character, or do anything of that nature. So it's not. Is that incorrect?
It reads until the NAS 0 until you pass also the length to constructor.
But if you were to construct it from a pair of iterators, it's not going to. Yeah. So I should clarify. If you just give it a single pointer to like a single car star, it will read until the end and look for a null terminating character. But there are other constructors you could use. Like there's a constructor that just takes a pair of iterators. That if you had an internal string representation that was not null terminated. But there is the constructor that takes a single car star will assume that it's a null terminated string and look for the null terminating character. Thank you, Nico. Okay. All right. I think we're going to move on. If there's more questions on this, let's save them to the end. Okay. All right. So next I want to talk about std optional. So again, with this like 2int API. So what do we do if the conversion from this string view to an int fails? Well, there's a couple options. We could return a default constructed int on a parse error. We could throw on a parse error. We could return false on a parse error, like, or return like 0 on a false error. We could return null on a parse, like return a null unique pointer on a parse error. None of these options I think are particularly attractive. In particular, this last one here where we're trying to use pointer semantics to add sort of like a state of, hey, this thing is not really valid. So in C++17, we have this new thing called std optional, which is a nullable object wrapper. And so it's in this header, include optional. And what it does is it adds a null state to the value that it wraps. And it provides smart pointer-esque interfaces for accessing the underlying entity. So this is a little unintuitive at first because it sort of looks and acts like a pointer, but it doesn't actually ever do any allocation. So it doesn't heap allocate, it owns its content. If you give it an optional t, t is just going to be a data member of the thing. And copying it's going to be, if t is cheap to copy, then copying an optional will be cheap. And passing style, if you pass t's by reference, you might want to pass optional t's by reference. And if you pass t's by value, then you should pass optional t's by value. Optional isn't just useful for error handling. There's a wide range of use cases. I keep discovering or being shown new ways that you can use optional. So let's talk about a few of those. So first, this is what using optional in that 2int example would look like. So first I've got my std optional here. We're going to try to I'm going to return this one if I have no int. And then I go try to use string stream to try to extract out of that string an int, and if I do, I go ahead and assign it to this optional, and otherwise, and if I don't, I just return the default constructed optional, which is in the null state. So if you just default construct an optional, it will be in the null state. So it's useful when you're working with types like int, which you can default construct, but they'll be in sort of this invalid state where who knows what the value of that int could be. It's also useful when you're working with types that might not even be default constructible. So I have this one example from a project I've been working on where we have this function depend that retrieves a value from a future using .then. And the idea here is that the lambda passed to .then stores the value of the future, which is passed as the argument to this lambda, into some variable r here in the outside scope that's captured by reference. So this lambda captures r by reference, and then it assigns it the value from the future here. And when I originally wrote this code, this wasn't an optional, and at some points this was used with a t that was not default constructible, and then the code broke because I was trying to default construct t here, and it was really just because I was going to assign to this object r here, but I needed to have a null state because I needed to have a state. I needed it to exist before I was going to assign to it because I was going to pass it into this lambda here. So I don't know if Mihao is still here, but one of my colleagues was like, "Oh, just make it an optional." And then when it's an optional here, it's added this null state so I can default construct it and then pass it in. And then at the end here, I just dereference the optional and move the value out. And then this will work for my types that are not default constructible. Yep.
First, I think you have a slide where you say return false and return true.
Sorry.
Did you have a type on the previous slide, on the before slide, when you say return bool and return integer?
That's possible. Let me take a step back. Which one? This one?
Step at time, one more.
Yep.
Here.
Yeah, you're right. This one should be take 2int and then have an int reference parameter and return a bool.
So the second, and on your example, you still define int outside of if. So there is no way to define I inside, in the initialization section.
Yeah, that's just because I'm reading it into the string stream here, but I'm checking whether that's that's valid here. I'm doing this. I see what you're saying, but the idea here is not that I'm not default constructing an int.
No. My question is about what you were talking about last hour, the previous hour. You said that if you see initialization section here, or for if, they cannot move I into initialization section from if. I is only used inside of the if.
Oh yeah, I could have, yes. I could have used selection statements, the if init condition here. Yeah, I think that's right. Yes.
You already use it. I don't think you can. That's why I'm asking. You already use it because you define it as STM inside. So then, can you define two? Can you define?
Oh, is it okay? The question is, can I define two variables in I don't believe of different types. I don't think so. I don't believe so. I don't think you could have int. I don't think you could both have an int and a stood string stream in the init section here. No. I have the. I think it's the same problem where you can't have more than two in an if. Sorry, what?
Just the option.
How to have just the option? Yes, then you can take the string stream out of there. You can have one of them in the init statement there. You can't have multiple ones of different types initialized there. Okay.
If you structure bindings, could you then get multiple variables of different types?
Yes, the answer is yes. If you like wrapped up all the things that you wanted to initialize into a tuple, yeah, that would work. So yeah, if you use like a temporary tuple, yeah, that would work. Okay, there, we found a way. Okay, all right. Any other questions on how we can use if-init condition syntax here? What's the space overhead of optional? That's a good question. It's going to depend on your implementation. It's not going to be nothing, but it's going to depend on your implementation and alignment requirements, I would assume. Right, but then you have to think about alignment requirements too. So yes, it is at minimum 1 bit, but it's going to be more than that because of alignment requirements. And it's never going to be nothing. Your implementation is not allowed to specialize it for types where maybe it thinks there's a way to represent that state in some unused bits of the actual underlying type. So it doesn't have any hacks for like pointers or anything like that. Yep.
Does it nest and use the optional to the optional?
You can, and so the question was, can you do like optional of optional? And I've had conversations with people about whether optional of optional is useful. I think if you're making like optionals of optionals, then it means that like you want to have more than just one extra state that you add, and there are better ways to do that. But yeah, you can do that. It works. You can have optionals of optionals. All right. Other questions on this? Okay. I'm going to skip past this one because that's got a lot of things that we just talked about. So one of the other use cases that I like for optional is using optional to express optional parameters to functions instead of having default parameters. So like here, this slice function, and I hope I have usage examples of it. Maybe I don't. Where I want to have both a start and an end, both of which could be sort of unprovided. So like you could just brace init either one of those, and that would be fine. But I don't want to like have them be default parameters because I'd like you to, like there isn't one of those that seems like a natural fit for me to be the default parameter. So I'll always make you specify all of them, but you can just brace init one if you just want it to be to just default to like the start or the end of the string. And so that's where you might want to use optional as sort of a way of having named but defaulted parameters. All right, next up, let's talk about variant. So, yep.
So with the default, if you default brace construct, is that the same as a standard null? Like, can you get into trouble where a default construct instead of passing an empty optional?
So the question was, if you default construct an optional, is the value std null opt?
Is it going to be should you use a std null opt instead of a default brace?
I'm not sure.
Because I've seen where you get problems where you return default brace could be an option with default constructed optional type.
Yeah, I'm not sure. I think we'd have to talk about that offline. Okay. Yeah. Yep. Sorry, can you repeat that one more time?
Sure. So if you want to provide just a string view, you've got the two options there. You invoke slice with a single argument, or do you need to provide the null option?
So the question is, do you need to provide the optional arguments here? Yeah, you do, because they're just regular arguments. So you do need to provide the start and the end arguments here. You need to call this function with 3 arguments. It's just that instead of just having these be ints where like there's a special value, like if it's 0, it'll mean this. Like I want an int with an extra state where the state can be that it's not 0, but it's this nullable state. Yes.
Answer the previous question about the default state. I think you can use stood none for that. That's also, I believe, the best practice. Instead of reset is deprecated, so you should actually set it to stood none.
The comment was that you should use stood none to indicate the default state for stood optional. And I'll take that on faith. I'm not sure myself, but I think that's correct. Yeah. Okay. Any other questions? All right. Let's keep going. All right. So variants. So before C++ 17, working with discriminated unions was not easy. We had this thing union from C, but it's kind of a pain to build anything that's type safe with it. So like, for example, here I'm trying to create basically the equivalent of like a variant with 3 different states where I have this type where I want it to either be an int or a double or a string and be able to switch between being one of these 3 things. But there's a lot of places for possible bugs here, and for a lot of maintenance overhead, like let's say that I add a bool type here later, but I forget to add a bool to this state type. And I've actually written one of these things many years ago for a large software project, and we started off with like 3 different states, and by the time I left there was like 20, and the enum was quite long, and it was just a giant source of bugs. And also there's questions about like, when you're using unions, do these constructors and destructors get run when you switch between states, and no, they're not going to. So union's not really something that you should be using in C++. It doesn't really respect the rules of types in C++. But it would be useful for us to have a facility for representing variants, and now we have one in C++ 17, and it's called stood variant. So like if I wanted to have this convert function here that converted a string from some representation to either a bool, an int, or a double, assuming that it fits one of those, you can just write stood variant, bool, int, double, stood string, and stood variant will be an object of one of these types. So it's a discriminated union. So it's in the header variant. Its interface is similar to boost variant. Some of the semantics are a bit different, and its access uses the visitor pattern, and I have some examples of that. So it doesn't use a heap allocation, and it owns its own contents. And it's like if you would want to if copying is cheap for all of these types, then copying would be cheap for the variant. And if you would pass all the types in a variant by reference, then you might want to be passing those variants by reference instead of by value. And it's just a variadic parameter pack here, so you can have as many things in the variant as you'd like. So like here's an example of visitation. So what I've got is this multiplier visitor here. So it's got 3 different overloads for its call operators, each of which takes something and turns it into something of that type that's been multiplied by 1. So like here for the string, it'll take, if you give it a string, and it will duplicate that string. And then for an integer, it'll just multiply it by n, where n is whatever this template parameter is. And for the array, it'll just multiply each element of the array by n. And then the way that you use visitors is with this stood visit function, where you provide it with a callable that is overloaded for all of the types in your variant, or that can be called with all the types of your variant. It doesn't need to be overloaded. It could be a call operator that's a template. And then visit will call the call operator with the type that the variant is currently in. So like here, I've got a variant where it's an int, so it will call this call operator right here. And then if I assign a string here, it will call this first call operator right here. Now, all of it needs to be, it will instantiate calls for all of the different options, of course, because it needs to dispatch at runtime to the correct one. You can write visitors a little bit easier in C++17 with if const expr. So here instead of writing a separate struct, I'm writing the same thing as a lambda and just using if const expr to pick the right operation, and then a static assert here if it's some other type. And there's also a nifty little trick you can do with variadic using declarations, which is a language feature I didn't talk about in the first part here, but I've got this struct overloaded here, which inherits from all of the template parameters that it's passed to, and then it does this variadic using declaration of the call operators of all the things it inherits from. And then there's this deduction guide here, so that it's basically just a quicker way of writing this without writing a constructor. And then what you can do with this is you can brace initialize this from a set of lambdas, and then this overloaded object will have a call operator, which is like an overload set of all three of these. Yeah?
Why we don't pass template argument for read function here?
Why we don't?
It will be blank.
Well, for right here where it's called?
Yes.
Well, the string, yeah, you're right. There should be an N there. Yeah, that's a bug in the slides. So yeah, I should have a Ingley brackets N right there. Yeah. So this is sort of my preferred way of writing visitors, because it's nice and fairly clean. And I don't, like, if const expr is nice and all, but I think this is a little bit nicer to work with. And there is going to, hopefully at some point, be a function called std overload, which would sort of work like this, but be a little bit cleaner. And this only really actually only works for things with call operators, not for any callable. All right. So another place where variants can be useful is if you're writing recursive data structures, for example, like a binary tree. So here I've got this is my binary tree structure, and then I've got this branch node type here, where a branch is going to have a shared pointer to a left, a shared pointer to a binary tree for representing the left branch, and then another one for the right branch. And then the tree itself is a variant, which is either the leaf types, the actual data type that we're storing, or one of these binary trees branch elements. All right, any questions on variant? Yep.
So let's say I have variant in long.
Yep.
So if my visitor doesn't necessarily have to have all three. Have one.
Right, so the question was, let's say that I have a variant of int, short, and double. And does my variant visitor doesn't necessarily need to have an overload for each. And that's correct. All that what needs to be true is that you need to be able to instantiate a call for each one of those types. That the callable that you give to visit you need to be able to actually make that call to each one. So it could be that it's a template function. It could be that there's a set of implicit conversions that will work. But even if the variant is not in one of the states, the variant's going to be in like the int state, let's say. When you call visit on it, the call for the short state and the double state still need to work, because the compiler's not going to know at compile time which one it's going to actually be made. Does that make sense? Okay. Any other questions? Right. It also needs to be non-ambiguous. Yes. Okay. Other questions on variant visitation? Okay, great. All right, the next one of these vocabulary types I'll talk about is std any. So what std any is it's a generalized type erasure facility. So like, what if you wanted to have like a heterogeneous vector? Well, you can use std any to build that. So like right here, the std vector of std any can store any object. So I can put a string in there, I can put a tuple, I can put in, so I could put std vectors of std any in there. So it's in this header any. It's type erasure for copyable objects. There are 4 main operations you can do with any. You can copy them. You can assign them some value, a value of some type t. You can ask whether an any contains a value of a particular type. So you can say like, hey, are you in? Do you have an int right now? And you can then retrieve a value of some type t using this anycast function. So any's will store their memory on the heap. They own their contents, and you should probably pass them by reference because they're being stored on the heap. All right. Okay. Any questions on this? Can you store a non-copyable type in any? I'm not sure. Yeah, I'm not sure. I would have to check. If you come up and ask me later, I will go and check for you. Okay. Next up, I'm going to talk about my favorite feature in C++17, the parallel algorithms. So prior to C++17, we had concurrency primitives and sort of low-level parallel programming primitives in C++, but we didn't really have any high-level interfaces for expressing parallelism. So something like this, like an OpenMP parallel for loop, we didn't really have any standard way of doing this. Now in C++17 we do. So the model is parallel versions of all of the existing standard library algorithms. So something like for each, the parallel version of that it'll have the same interface, except that the first argument will be this thing called an execution policy. So this is one of the 3 that are in 3 execution policies that are in C++17, and it indicates what type of parallelism is allowable for the operations and the data types that you're passing in. So like this would be roughly the equivalent of what we've written here on the left with OpenMP pragmas. So like this is a serial sort, and then this is what a parallel sort would look like in C++17. So for all the algorithms, it's these new parallel algorithms are the same API, except the first parameter is this execution policy thing. These algorithms live in the same places that their current algorithms live, so algorithm and numeric, and the execution policies are in the execution header. The input iterator requirements for any algorithm that currently has an input iterator requirement, the parallel version bumps that requirement up to forward iterator because that alleviates a lot of implementation concerns. We're not really sure how to parallelize a number of the algorithms for input iterators, so we decided to bump up the requirements for 17 and leave that design space open for the future. And the complexity guarantees are relaxed for some of the parallel versions of algorithms where we don't believe that there is a way to implement the algorithm in parallel with the same complexity guarantees that are given in serial. And there are some new algorithms that are designed for parallel programming. So there's reduce, inclusive scan, and exclusive scan. And then there's these 3 fused algorithms, transform, reduce, transform, inclusive scan, and transform, exclusive scan. So the execution policy parameter, it sort of describes the how of execution. So it like answers the question, is parallelism allowed? What restrictions must be respected by the algorithm? And at some point in the future, this facility will be integrated with executors, which is a richer way of describing where work should be created, on what resources should execution agents be created, that is hopefully being planned for C++20, and there's ongoing work on a technical specification for that. And right now, though, there's 3 execution policies in C++17. There's std seek, which indicates that you don't want any parallelism, you just want sequential execution. There's std par for parallelism without any reordering, so it's like SIMD systems like GPUs. And then std par on seek, which is for parallel and unordered execution, so something like a SIMD system where you would want thread parallelism and also vector parallelism. So the difference between std_par and std_par and seek is that with std_par, operations are indeterminately sequenced with respect to each other within the same thread. With std_par and seek, the operations are unsequenced with respect to each other, and they may be interleaved. The interleaving is the key thing here, that basically std_par and seek says that you're giving permission for like your process function here to be interleaved. Because normally a library would not have capabilities to go and say, hey, I'm just going to unleave this function, interleave this function that this user gave me. So let's see, you've got a few examples here. So these are some examples with some of the new parallel algorithms. So this is how you'd write a serial dot product in C++. Just, I've got two vectors. I want to do x, 0 times y, 0, yada, yada, yada. And with the new algorithms transform reduce, you just write this. And so transform reduce does a transformation, so applies some unary operator or some binary operator in this case, and the default is to do multiplication, and then it reduces the sort of pseudo sequence that's formed from the transformation. So that would be the plus operator, which is the default there. So this is a parallel dot product in C++ 17. And let's see, did I print another one? And then this is a version with, this one. So this is the full version without any of the operators defaulted of transform reduce, and this is the unary version. So the execution parameter, then this is the input sequence initial value, and then this is our reduction operator, which is addition here. And then here we're doing a vector norm, so the transform operation is just squaring whatever the input is here. So this is just examples from the new transform reduce algorithm. Any questions on this feature? Okay. So next feature, the file system library. So prior to C++ 11, there was no standard support for file system access or querying in C++, and depending on the system you're on, these APIs can differ greatly, and I think they tend to be quite ugly. This is what copying a file in a directory looks like with the Windows APIs, and I've always hated these, especially given that they're quite different APIs for operations that seem like they should be quite similar. In C++ 17, you can do this in a portable way using the new file system library. I should note this fs here I'm just using as an alias for the full name of this namespace, which is stud : file system, which does not fit well on slides and is a little bit unfortunate. So this is not only, I think, portable, but it's more user-friendly. So it's contained in the file system header. And as I mentioned, that's the convention I'm using in these slides and that a lot of people have been using. It's based on the Boost file system. The interface is primarily non-member functions operating on path objects. So the main primitives of this is the path class, and then there's directory entries and directory iterator for moving through directories, and then file status is the platform agnostic representation of metadata. So there's 4 major sort of classes of operations that you can do with the file system library. There's path creation and manipulation, directory iteration, recursion, and then file and directory, metadata query, creation, removal, and modification. Like this is an example of what it looks like displaying the contents of a path in C++ 17, and this is not recursive because it doesn't fit onto a slide, but basically we take the path, we print off the path, and then if it's a directory, if it's not a directory, then we're done. If it is a directory, we go and create a directory iterator from the path, and then we iterate through each thing in the directory, and we'll go and print off the size using one of the metadata query functions. So there's a fairly large and rich API, not something I can cover in sort of an overview talk. but it's worth going and taking a look at. The interface is sort of, it's not that it's based on POSIX, but the Boost file system API draws a lot of inspiration from the POSIX API and then maps other file system APIs onto those interfaces. Yep.
Are there important differences between the standard file system and the Boost file system that some of us are familiar with?
The question is, are there differences between the standard file system library and the Boost file system library? The answer is I'm not 100% sure, but I'm almost positive there are differences, and I believe some of them are notable. If you want, we can talk a little bit about afterwards, but I'm not certain on all the details of that. But it's worth looking at. You shouldn't assume that it's the case. Yes?
One important thing, if you convert from Boost file system to standard file system, and your program recompiles, it might still behave different. We change behavior without changing the API. So beware.
So what Nico pointed out is that even if your code still compiles after just changing Boost file system to Std file system, the behavior might be different because while we've kept APIs in some places, the semantics have not necessarily been kept, even if it's the same APIs. So don't assume that it's the same library. Yes, question there.
What kind of strings are used as strings or white strings, or is platform dependent?
The question is, what type of strings are used as the basis for files, strings or wide strings?
As names of paths, yeah.
I'm not certain. I believe it's platform dependent. I'd have to check though. I'm not certain. Other questions here? Okay. How much are we doing on time? Okay, great. All right, so next thing I'm going to talk about the polymorphic allocators in C++ 17. And I'm not going to talk a lot about this, but fortunately there are 5 talks about allocators this week at the conference. So if you want to learn more about allocators, there's plenty of content. So before C++ 17, the old allocator model we had caused an explosion of instantiations of all of our allocator-aware constructs. So if you have a whole bunch of different allocator types you were going to use in your program, you would need to have a whole bunch of different instantiations of Std vector. And this can be a problem once you have a fairly large code base. So in C++ 17, we have a polymorphic allocator type that type erases a abstraction of a memory allocator. And the abstraction, it's this thing called memory resource, and I have another slide on that. And you can implement your own. There's also some that are provided by the standard. So there's I think I actually have a list here. Yep. So there's a new delete resource, which just uses the global new and delete. There is a unsynchronized pool resource, which is a thread unsafe memory pool. There's then a thread safe memory pool. And then there's a monotonic buffer memory allocator. And so all of these live in the PMR namespace. And also in the PMR namespace, there are aliases for all of the standard library constructs that are polymorphic aware. So like Std vector int Std PMR allocator int is Std PMR vector. And so what this gives you the capability of having just one vector type that you're using in your code base that has different types of allocators backing it. Okay. I'm going to skip through that one because we're a little short on time. Okay, so improved insertion and splicing for associative containers. So map, multi-map, unordered map, and unordered multi-map now have try in place and insert or assign functions. So these interfaces are designed to make it easier to deal with operations on maps that access existing keys. So in place, which is a pre-C++ 17 map API, if it takes the key to value, if the insertion failed, was this P moved here, And would you be able to go and move from this P here? Try and place guarantees that if the insertion fails, P wasn't moved, and insert or assign returns the info as to whether the insertion failed as a pair of iterator and bool here. So that you don't have to wonder, did this operation here actually insert or assign this key, and what iterator is the key at? It gives it back to you now. And we also now have a way to merge maps. So if you have a map, if you have like two maps and you want to merge them, you can just do m0.merge m1. And the merge doesn't overwrite existing keys. And I have the complexity guarantees and notes in the slides if you want them. I'm not going to read them out, though, because it's kind of difficult to read them out. And this is for all the associative containers. And let's, yep. Yep.
How does it guarantee that there is no move? It sees the move.
Not that this move doesn't happen, but whether the thing is actually moved out of inside by the operation. Whether, like, if it can't insert it, does it actually consume the object?
If we moved and then P already.
Sorry. I think you're right. Yeah, that should not be a move. That should just be a P there. Yeah. Sorry, my apologies. You're right. That should just be a P there. Yes. Okay. Merge. Let's see. This last one. So there's also now interfaces for the associative containers to do node-based insertion and extraction. So you can take a node out of one associative container and insert it into another one. So the APIs, you can do like this .extract function, and there are type defs in the associative containers to an implementation defined type that is the node type. And that node type, you can like do a few things with it, like you can get the key. It doesn't expose too many implementation details. And then you can move nodes removed from one map into another map, for example. You can't move nodes between containers of different types, of course. Let's see, got a couple other quick ones. So the special math functions, which were in a separate international standard that's been around for a few years, are now part of the main C++ standard. So they're in the C math header, and it's this list of math functions here. And all right, variable. There are now these _v variable templates for meta functions. These are defined for all the type traits. So, like right here, instead of writing stood is integral t value, you can just write stood is integral _v. It's nice, just a small convenience feature. And in C++ 11, let's say that we wanted to write an all integral type trait, which is true if all the elements in a parameter pack are integral and it's false otherwise. I commonly run into this pattern when spheaning on parameter packs. And we now have this bool constant in C++ 17. And this is pretty convenient. You can use this and fold expressions to express this same pattern right here, although this bool constant, this won't short circuit properly. And what's going on here? Yeah, so there are these Boolean logic meta functions as well. So because this one will not short circuit properly, there is a stood conjunction meta function that will. And we also have a stood disjunction and a stood negation. And they're the moral equivalents of these operations here. And all right, that brings us to the end, and I think we're pretty much out of time, so if you have some questions, come up to me afterwards. Okay.